share. So share desktop. Okay. So everyone can hear me okay? Good. And then this title screen is up here. So I can probably just switch this to a laser pointer like this. Okay, great. Okay. Yes, Dr. Vandrest and my supervisor, Dr. Nicknoff. Yeah. Hey. I'll be right back, Dr. Atkinson. Okay, yeah, feeling good, ready to go. Okay. Mm. Thank you, Dr. Atkinson, for that wonderful intro. Um, So yeah, today for my 7P95, I'll be talking about chiral induced spin selectivity. So this process is primarily a phenomenon that's been discovered that deals with electron transfers. So as we know, electrons are transferred in most organic or biological compounds and organisms, and is used for the transference of energy as well as information. And we've kind of been asking a question here, or scientists have been asking a question of why has nature chosen to use chiral molecules instead of more wire-like molecules for the transmission of electrons through these proteins. And as you can see here in photosystem 2, there's a plethora here of helices and corkscrew-shaped compounds. And it's a mystery, or at least it used to be, of why did nature over billions of years decide to develop these corkscrew helices instead of more rigid structures. And as we know in our electronics today, we use wires for the conduction of electricity. But one group that was very interested in the answer to this question of why nature uses chiral molecules for the transference of electrons. One group was Dr. Newman's group, and he published in 1999 the theory of chiral induced spin selectivity, which was an answer to this question. His seminal report on the asymmetric scattering of polarized electrons by organized organic films of chiral molecules laid out the fundamentals for the CISS effect. And the CISS effect primarily has two major actors, chirality and spin. And before we get into kind of an understanding of the CISS effect and the applications that it has, I think it's important that we first delve into these two main actors. So the first, chirality, as mostly chemists and biochemists here, we're familiar with chirality in that it is a fundamental asymmetry in the geometry of molecules and geometry of shapes, in that one mirror image or the mirror image of a compound is non-superimposable on itself. And the great example is the human hands, where you can have a shape that, although seemingly identical, when undergoing a parity inversion or a rotation or an inversion through a center of symmetry, you can arrive at a shape that is not the same starting compound. And hands are a great example of this, as well as the helices, like these corkscrews here. If you reflect them across a mirror plane, you don't get the same structure. And it is very important for chemists, and especially those who deal with pharmaceuticals, to be aware of these inconsistencies. The classic horror story is the drug thalidomide, where one enantiomer of the drug was used as a sedative to help pregnant women relieve symptoms of morning sickness. And the other enantiomer of this drug, the right-handed version, was actually toxic to the development of the fetus. And at the time, it was thought that maybe there's or there wasn't given proper precaution to the separation of enantiomers, and this led to very tragic results. Now, so this is the fundamental thing, is that these enantiomers are not the same compound, despite their seemingly similarities in connectivity and composition. So that's chirality. And electron spin now is a much more subtle quantum mechanical aspect of an electron that is a little bit more difficult to bring into this box here. So I found this somewhat facetious quote online that says, to describe electron spin, imagine a ball that's rotating, except it's not a ball and it's not actually rotating. And I think that's perfect for just kind of showing the how our classical interpretation of certain aspects like spin, these classical understandings start to break down when you're trying to apply them to the quantum mechanical realm. And this is especially true for spin, and it's an unfortunate naming. So the naming itself, though, does have some use in that it can help us kind of begin to understand some of these subtleties of the quantum mechanical spin. In that, if you imagine the electron as a ball, it can rotate either to the left or to the right, And if electron is a distribution of charge over some sphere, this is thinking purely like classically, then if you were to rotate this ball of charge either to the left or to the right, you would induce well, the acceleration of these charged species would induce a magnetic dipole, and and as well as maintaining an angular momentum of the electron. And this is what we observe with spin, where if we were to rotate a charged ball, we would generate a magnetic field. Now, this breaks down, as I was kind of saying, in the sense that the electron doesn't really have a radius in a classical sense, and these rotations and these angular momenta and magnetic dipole, they're quantized. But in the idea of a ball, you could rotate that ball in any direction. But with quantum mechanical spin, these are quantized, discrete representations in a binary, essentially. So I think it's important to kind of go over a review of spin here. And the first thing to understand is that the spin of an electron is an intrinsic property of an electron. Similar to how an electron has a certain mass and a certain charge, the spin angular momentum, along with that magnetic dipole along its spin axis, is a quantized feature, or sorry, intrinsic feature. Now, spin itself was kind of a latecomer to the quantum mechanics party. Even after Schrödinger had developed the Schrödinger equation in 1925, and everything seemed to be lining up fairly well experimentally with the emission lines, the spectral emission lines of the hydrogen atom. There was still some mysteries, experimental mysteries, that were still unresolved. For example, the Stern-Gerlach experiment showed in 1921 that if you were to pass a beam of atoms, a beam of silver atoms, through a magnetic field, you end up with a very odd result. You end up with a splitting of the beam into two discrete positions. Now, if you were to think of this is very strange, because if you were to think of, first of all, of just the silver atom by itself as having a dipole, geometrically you could imagine that you could orient that silver atom in any direction, and you would assume that you would get the result shown here in 4, where there would be an even distribution of atom impacts on the detector plate, just based on those random orientations. However, that's not what they observe here. They observe two discrete patterns. And it is important that they use silver atoms because the silver atom just has that one unpaired electron in the 5s orbital, and this basically is a large neutral electron. You can think of the silver atom as a large neutral electron. So this is a purely electron-based effect that we're observing here, where we get the splitting into two discrete patterns. And the Schrödinger equation, although it was very good at predicting things like I said, the emission lines of spectra and other calculations, like lining up theory with experiment, it couldn't account for these. It couldn't account for this effect. So there's still a mystery. And another experimental mystery was like the fine structure of the hydrogen emission spectra, where we saw some splitting under magnetic fields. This was also like not accounted for by the Schrödinger equation. So in 1924, Wolfgang Pauli proposed a new quantum degree of freedom, ms, with two possible values, and he stated that no two electrons can have the same four identical quantum numbers. So we have our principal number, our principal quantum number, our angular momentum, magnetic quantum number, and spin quantum number. And the spin quantum number is was later identified by Ralph Kronig and George Ulmbeck and Samuel Goodsmith as the proposed electron spin. And sorry, it's just if everyone can mute their mic. I'm just hearing a little bit of an echo, and it's just kind of hard to talk. But yeah, thank you. So Paul Dirac later formulated this electron spin as being either plus one half or minus one half. And he saw this as an intrinsic form of quantized angular momentum. In 1928, he derived the relativistic wave equation, which described all spin one half particles with mass. And uh, following this, we're now able to see a description of the electron, in that if we have two electrons with opposite spin, like I said, these spins are quantized into their either, you can see them as either plus one half or minus one half. If we have two electrons, in the absence of a magnetic field, they're degenerate and have identical energies. However, as we apply a magnetic field, we then split the energy levels, and we destabilize one electron, you can see here, and we stabilize the other. And this is just based on that electron spin orientation relative to the external applied magnetic field B naught. So with a large magnetic external field, the spin that is parallel to the magnetic field will be stabilized and reside in a lower energy level, and the spin that is anti-parallel to that external magnetic field will be destabilized up here. And this is known as the electron-Zeeman effect. And we can account for this difference in energy level with electromagnetic radiation. And we can induce transitions between energy levels with microwave in this case. And this is really the fundamental setup for spectroscopy techniques like EPR, whereby we can determine attributes of a paramagnetic compound based on the energy needed to account for this transition of a known magnetic field Zeeman splitting. So, with an understanding now of spin and of chirality, what is the CISS effect? And essentially it's that as electrons pass through a chiral molecule, one spin is preferred over the other based on the handedness of the molecule. Essentially, chiral molecules are spin filters, and you can see here in these animations, we have one chiral molecule and the other enantiomer, and we're able to selectively transmit electrons through these chiral molecules based on the spin of the electron, the intrinsic spin of the electron. So, the early history of this technique really began with the discovery of molecular chirality in 1848 by Louis Pasteur. And he painstakingly separated the left and right enantiomers of tartaric acid by visually identifying them based on their crystal shapes. Now, based on previous work by Jean-Baptiste in 1812, he was able to identify them as separate enantiomers based on their specific rotation. So if he created a solution of one enantiomer and dissolved it in solution and recorded the specific rotation, it would rotate linearly polarized light in one direction. And if he dissolved the other enantiomer in solution, it would rotate that linearly polarized light in the opposite direction. A racemic mixture of both crystals would induce no rotation. So this was the discovery here of chirality, and since then there's been much work done. But another interesting interaction now, so if CISS is an interaction between electrons and chiral molecules, then this is now kind of the asymmetric interaction of photons with chiral molecules. We can see showing up in circular dichroism, where it's been established that the chiral molecules will absorb left and right circularly polarized light by differing amounts. And this has found great applications in biochemistry specifically, where we can monitor the asymmetric absorbance of one circularly polarized light over the other in order to determine enantiomeric excesses, as well as certain structural properties of biochemical compounds. And we can see here a CD spectrum, where if we were to have a totally racemic, a totally non-optically active compound, we would just have a line at the zero. But due to this optical activity of chiral compounds, the interactions between the asymmetric interactions between photons and chiral species, we can see that we get an interesting variation in our absorbance spectra here. So um, this chiral this difference in circular dichroism kind of brings up an interesting question of why is life chiral? Why are there why is there a preference in the human body as well as in like life in general? Why is there a preference for one enantiomer over the other? Um, if you were to think about the conditions, billions of years ago when life was evolving from abiotic material, you would suspect that there would be no asymmetry in the abundance of different chiral compounds. If we were to, for example, synthetically try to create L-alanine or synthetically try to create alanine from simple materials that were available, or that we suspect were available and at the early development of life in the Earth, you would get racemic mixtures of both enantiomers. So why is there such a chiral excess of one building block? And we see this, for example, with L-alanine, where L-alanine is used in many proteins, and as a fundamental amino acid, where the D-alanine is much less frequently observed in nature. So this whole idea of the asymmetry of chirality in nature is known as homo-chirality. And it's interesting to think about this question because, at least in relation to the CISS effect, because the investigation into this question of why has nature chosen one enantiomer over the other, inadvertently led to the development of the CISS effect, and I'll show you how. So to rephrase this question, why has nature chosen one enantiomer, we can think of it as, does nature recognize parity transformations? Now, parity transformation is essentially, if in 3 dimensions, if we were to take an x, y, and z coordinate and just find the inverse, then you would be performing a parity transformation on a structure. And to do a parity transformation on a chiral compound, you end up with the other enantiomer, which, as we know, is non-superimposable on itself. So, does the laws of physics, are they aware of these parity transformations? And another way to think about this question was, if there was a mirror universe, and this mirror universe had all the identical, fundamental constants and forces of nature. However, it was just a perfect flip of ours in terms of it's a mirror representation of ours, and all the enantiomers all the left-handed enantiomers are the right, and all the right are the left. Would there be any way to tell which mirror universe we are in? Is there any experiment we can do? And if you think about it, the answer seems to be no, right? Like, what experiment could you do to determine which universe you're in? If you were to perform some chemistry experiment, then all the electrostatic forces, gravity, constants like the speed of light and Planck's constant, these are all the same no matter the geometry of molecules. So it seems to be that nature is symmetric in this regard. However, surprisingly, it's not. And nature does seem to be aware of chirality. And this was the discovery of parity violation. So Yang and Li, who won the Nobel Prize in 1957, they looked through the literature and they saw that for the gravitational force of gravity, the electrostatic force, the strong nuclear force, there was parity conserved. Parity was conserved. But for the weak nuclear force, it was unsure at the time if parity was conserved in this as well. And they proposed some experiments, and later that year, Madame Wu, the designer of the Wu experiment, proved that the weak force, which is a fundamental force, one of the 4 fundamental forces of nature, it violates parity, and it's asymmetric. And this was a huge revelation because it means that, in a way, nature is aware of chirality, and our universe is chiral on a fundamental level. And just kind of a schematic representation of this, of how strange this would be, was if we were to have a two clocks, and you can see here for the parity symmetric example, the mirror image of the clock on the left here, the arms move in the same direction relative to the mirror plane. However, in this parity asymmetric way, we can see that the arm of this clock actually moves asymmetrically to its enantiomer, and this is how the weak force operates in our universe. It's not symmetric in that sense. So this now kind of leads to the interactions that are the fundamental basis for the CISS effect, because electrons don't interact identically with chiral molecules. And a great experiment that kind of answers this previous question of why has nature chosen one enantiomer over the other for the building blocks of life. A great experiment that describes this reasoning was this one done here in 1968, where they observed the beta minus decay of strontium 90 atoms in the presence of 2 enantiomers of tyrosine. And shown here in this Feynman diagram, a beta minus decay is essentially the conversion of a neutron into a proton, and this is carried out by a W boson, which results in the formation of a single electron with a specific spin. So they all have the same spin, and it was observed over several months here that when exposed to this spin polarized electron emission, one enantiomer of tyrosine decomposed asymmetrically to the other, and you can compare it to the control in blue, and we can see that there is indeed an asymmetry to this decomposition over time, and this in a way answers the question of, or it may be a potential reasoning for the answer to why we observe an abundance of one enantiomer over the other in biology. So this now sets up the search for spin effects, and if we can see that polarized electrons can asymmetrically affect chiral molecules, then maybe chiral molecules can polarize electron beams. And this experiment carried out by the Farago group set out to determine just that. If we had some chiral molecule like the camphor here, the R and S versions of camphor, could we, by passing an unpolarized beam of electrons through the camphor molecules in gas phase, could we observe some sort of polarization effect? And using this experimental setup, they determined that via scattering, there was actually very little amount of polarization, and it was within the error of margin. And the experiment essentially showed that there didn't seem to be any polarization effects, at least in this sense. However, when looking at absorptivity, it was determined that there is some sort of electron dichroic effect, in that by passing a unpolarized beam of electrons through, again, a fully chiral gas, we observed that there was some asymmetry in that the electrons which are spin parallel to the direction of the beam, which are IP, is different than the electrons that are spin anti-parallel to the direction of the beam, which would be minus P. And for this asymmetry parameter, if you'd imagine that there was 100% polarization and the gas acted as a perfect spin filter, not allowing any electrons to pass through that were not parallel to the beam, you would get an asymmetry of 1, because the I minus, or the minus P, would go to 0 on both sides and just be IP over IP. And just to give you an idea of some of the values you would get, if only one electron was in the opposite direction, you'd get slightly less than 1. And as you increase the amount of electrons that get through that are not being polarized, you decrease this number here, 900. And then you see here with only one electron being polarized for every 1,000 or every 2,000, you get an asymmetry parameter of 5 to the minus 4. And that's actually kind of what they observed. About 1 in every 2,000 electrons were being spin polarized. You can see here that they adapted the previous work of using the chiral molecules, of course, and using like a bicyclic chiral molecule similar to camphor. However, they used these hydrofluorocarbons shown here, and these hydrofluorocarbons were complexes, were lanthanide complexes, and they believed that it was due to the high degree of spin-orbit coupling that you would see with these high atomic weight elements, that you'd get these asymmetric results, where at low electron energies, you get a great deal of asymmetry based on the enantiomer that your gas is comprised of. So this was an interesting result, and it really led to the development now of Dr. Newman's work and the CISS effect, because he decided to do something that was very different than what was expected for this type of research at the time. Instead of using gas phases, which many groups were working on, he decided to do Langmuir-Blodgett, thin layer Langmuir-Blodgett deposition onto a gold surface. And this is essentially the act of either depositing singular molecular sheets of a material on a compound. And as you can see in this little animation, you're able to get very structured, organized layers, and you're able to maintain a very good consistency between the layers. They did specifically the Z-type deposition, which allows for these hydrophilic heads to all be oriented in the same direction towards the gold substrate. Now, this was also interesting because previous to this work, it was thought that, for one, you need very high atomic weight atoms to induce the chiral, the CISS effect, right? That spin orbit coupling would be very small in carbons in carbon atoms, as opposed to like the lanthanides. And in addition to this, it was believed that you need to have a compound that is strongly chiral. And when they say strongly chiral, they just mean that if you were to take the one enantiomer and overlap it with the other, you should have a large degree of a large portion of the molecule should not be superimposed on itself. And as you can see here, we only have one chiral center and then a large achiral component to this molecule. So it doesn't seem like it would be very good at spin polarization. However, they found that it was very good at spin polarization, in fact. And by passing polarized beams of electrons that were emitted from the gold substrate through the chiral molecules, the 5 layers of L-styrol lysine, they observed that there was actually quite a high degree of asymmetry, 0.12, which was like 1,000 times larger than those that were reported in the gas phase studies. So just some additional information about this experiment. They used right circularly polarized light and left circularly polarized light because it was determined earlier that if you have these different circularly polarized lights incident on a gold substrate, you induce the emission of photoelectrons that are also polarized. And it was determined that with right circularly polarized light, you could create electron emissions that are electrons that are parallel to the momentum of the emitted photoelectron. And as we can see here, with a polarized beam of electrons, we have a much higher degree of transmission through the chiral molecule, as opposed to a polarized beam that is not in the direction of the emitted photoelectron. And in B here, we see that a 1% a 1% contamination of the other enantiomer removes this effect fairly significantly. So it was now understood that um, you can get a transmission of electron, you can get a polarization, a spin polarization of electrons by transmitting them through chiral molecules. And there were subsequent experiments done here where they used light to excite these cadmium selenide nanoparticles, which were attached to chiral molecules. And this excitation of the nanoparticles would result in the emission of electrons, which would transfer down to the gold substrates, which we were absorbed to. These chiral molecules were absorbed to. And then by using a Kelvin probe, which could apply an opposite potential difference, an opposite voltage, they could measure the amount of voltage needed to bring the current to zero. So if there was a lot of electrons being transferred through the chiral molecule, then it would take a higher voltage to negate that current. And we can see here for the chiral substrates, it takes a much larger voltage to negate that current induced by the excitation of electrons from the nanoparticle. So the picture is starting to come together now of why nature has chosen chiral structures. These are highly efficient electron transfers, and they're polarized, which eliminates electron backscattering, which can occur. Um, and if you think about it, it makes sense, because if there's any heat produced from these electron transfers, where there's billions of them occurring, every second in organisms, any small amount of heat will add up quite quickly. And if there's heat around, very sensitive proteins, you end up with denaturation, which can destroy these functions which are critical to life. So it is of evolutionary imperative that these electron transfers be as efficient as possible, especially when they're taking place over such long distances. As you can see here in photosystem 1, we're getting electron transfers over 7 to 10 nanometers, which on the scale of an electron is huge. So the theory behind why this effect occurs can be explained using essentially from a perspective of the Lorentz force. And in that, if you were to move a charged particle through an electric field with a certain velocity, we would develop an orthogonal magnetic field. And in the structure here, where we can see that we have a chiral molecule with a certain helicity, um, the cross product of the um, speed vector and the electric force vector, which is applied from the chiral molecule, would generate a magnetic field perpendicular to both, or orthogonal to both, and it would be along the axis of the chiral molecule. And depending now on the magnetic dipole of the electron, the dot product of that electron with the magnetic field, which is now coupled to, would exert a force which favors the direction, or which favors the spin of one electron over the other. As you can see here, this orange electron ball represents a transfer through a chiral molecule, and this black arrow represents a spin, which is anti-parallel to the induced magnetic field as this electron processes through the chiral molecule. And the magnetic field that's created here is actually quite strong. The exact derivation of the electrostatic vector from a chiral molecule is not included here, but if an electron with a velocity or a speed of about 2% the speed of light were moving through an electric field of 4.5 times 10 to the 11 volts per meter, it would generate a magnetic field of 3 Tesla. And that's a very significant magnetic field. And this is what creates this spin polarization, where you need an electron that aligns itself with the magnetic field to more efficiently transfer through a chiral molecule. Now, this theory can be explained in another way, the toy model. And in the toy model, you can think of two electrons as having either spin up or spin down, and you can represent them as a flag, which is blowing in one direction over the other. And as shown here, these two electrons are degenerate in that they have the same energy level in the absence of any sort of wind. However, if we were to put this electron in motion, as represented by the car, which is moving, from the right to the left, we can see that we create a wind, which stabilizes one spin, the flag to the right, over the other, which would be the flag to the left. And the wind in this case is our magnetic field that is created by the motion of the electron through the chiral molecule, through the electrostatic force E chiral. And this has an interesting side effect in that what would happen if an electron is elastically backscattered? And this is a phenomenon that occurs in wires where since there's definitely in a wire in an electronic compound, there's a potential difference between 2 points in the wire, and this induces the flow of electrons through it. However, occasionally electrons will be scattered opposite to the direction of the flow, and this reduces the efficiency of the system and creates heat. And what happens in a chiral molecule if an electron is backscattered? Well, it would induce it would attempt to induce a change in spin in the electron, since now the other spin would be stabilized. However, this is a quantum mechanically forbidden process to flip the spin of an electron. So this dramatically reduces the chance of backscattering in chiral molecules because of the forbidden nature of this electron spin change. And the little animation here kind of shows that in metals, we don't have any, we can't account for this, and that's why a great deal of heat is produced in thin metal wires, since the electrons can be backscattered elastically. So this has some very interesting applications in the electrolysis of water, for example. The electrolysis of water is a very well, it could be potentially very useful if we're able to take simple water, which is everywhere, and produce hydrogen gas, which can be used for fuel cells from it. It would be amazing if we could do this with low energy requirements. However, the potential needed across these two electrodes is quite high. And what they found is that if you coat the anode of these two electrodes with a chiral molecule, then you would produce only one spin of electrons through the anode, and this would actually reduce the electric potential needed to induce the electrolysis of water. And so why is this? To better understand, we need to think about the products of water electrolysis, which is hydrogen gas and oxygen gas. And oxygen has two stable molecular electron states, either the singlet state shown here, as well as the triplet state shown here. As we see in this highest occupied molecular orbital, in the singlet state, the electrons are paired anti-parallel to each other, and in the triplet state, these degenerate electrons are parallel to each other. And the triplet state is the most stable, and it would basically be it'd be the preferred product. However, due to the unpolarized electrons that usually come off of the electrodes in typical electrolysis, you get a mixture of both. However, if you polarize the electron beams using chiral compounds, you're able to select for one spin over the other. and this allows for a reduction now in the potential difference needed to create the triplet water. Um, and it eliminates that need for overpotential, or it significantly reduces the need for overpotential. So another added benefit of this is that it reduces the formation of electron or of electrolysis byproducts. One of the byproducts of electrolysis that's unnecessary is the formation of peroxide, and peroxide results in the formation of both in the if you reduce these hydroxide anions, and you end up with opposite spin radicals, then you can form peroxide. However, if the electrons that are being created are all spin polarized, then you significantly reduce the yield of peroxide in your water electrolysis process, which is highly desirable. Another really interesting application is that we can use it. Oh, sorry. Just to conclude, there's been really good experimental results shown here, where if we coat the electrode with a chiral coating, we can see that over the as compared to just an achiral coating or no coating at all, we can see a large increase in the amount of hydrogen gas produced over the same period of time. Just showing the effectiveness of the chiral induced spin selectivity effect. And another really interesting application is enantioseparation. So as I discussed earlier on in the presentation, it's important for us to be able to separate chiral molecules, thinking back to the thalidomide molecule. And a means of separating chiral molecules that is generic and that is widely applicable would be highly valuable to the pharmaceutical industries. And there's been a 2018 report here in Science where they show that they can use the CISS effect to actually separate chiral molecules. Now, how this works is that when a chiral molecule, let's take the left and right-handed enantiomers of this helix, when these chiral molecules approach some substrate, they are charge polarized, as indicated by the delta minus and delta plus. Now, this charge polarization induces a spin polarization in the chiral molecule due to the potential difference driving electrons through the molecule and one spin being preferred over the other. So we see the separation of spin states from the top to the bottom, and this separation in spin states now allows for an asymmetric affinity for adsorption to ferromagnetic compounds. So what that means is that the chiral enantiomer, which would result in spin polarization of one form shown here, the low spin form, will preferentially bind just due to the coupling of the molecule substrate, and it will preferentially bind compared to the high spin situation of the other enantiomer. So essentially, we can use magnets to separate chiral enantiomers, and this was beautifully shown here in this experiment, where they used this apparatus, which is essentially two magnets sandwiching a solution of a racemic mixture, and by inducing or by applying one magnetic field, they're able to show the preferential adsorption of one chiral compound as opposed to the other, and they basically just measured the cyclic dichroism, the CD spectra of the mixtures, and they found that they were able to preferentially absorb one enantiomer over the other, just using magnets. So, in conclusion, chiral molecules act as electron spin filters, reducing backscattering and spin polarization of electron currents. Spin orientation is coupled to the molecular frame, meaning that we can get a firm grasp now on spin just by manipulating these molecular structures. And new avenues in chemistry, physics, and biology are opening up as a result of the broad implications of the CISS effect. And With that, I'd like to express my thanks to everyone who joined and who listened to my presentation, and open to any questions and comments. Thank you. Oh, okay, good, good, good to hear. Oh, oh, that's fine, that's fine. It's all good. Yeah, all good. Hmm. Hmm. Sure. Hmm. Sure. Right. So yeah, spin is either up or down, and basically that's referring to this intrinsic angular momentum, which is quantized into either h bar 1 over 2 or minus h bar 1 over 2, and this was just a result. Mhm. Mhm. Um, I, the angular momentum, I believe, of the electron, in that it oh, mhm. um, mhm. Um, oh, plus one, like ms, like the quantum number of ms. Oh, hmm. Mhm. To calculate the value of the angular momentum. Um, um, to calculate, sorry, the I'm not sure I understand the question. Sorry. Hmm. I think it would be, oh, like ml, like m sub l, if the orbital, yeah. Hmm. Hmm. Yeah, I think I have. Sorry. Yeah. Is oh s, yeah. Okay. Hmm. 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 Um, what property of the angular momentum does this describe? It describes the orientation, or hmm. 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 Right. Hmm. Right. Okay, I see that. Mhm. 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 I imagine that it's very small. No, no, I didn't. I didn't do that. But I imagine that it'd be very small. Um, but just multiplied, I would say, over all the processes that were occurring in the organism, it would add up. Um, uh, mhm. 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 That's enough. Yeah. Mhm. That makes sense. Yeah. Mhm. Mhm. Um, just due to the transition from one atom to another within the molecule. It just in the paper I read, they described that it would be about 2% the speed of light moving through this chiral molecule. Um, yeah. Hmm. No, not so slow. Right. Hmm. Hmm. Very low. Okay. Um, yeah. You're right, and also I forgot to mention here that the radius of the like the helical path too is inversely proportional to like the produced magnetic field. So with very small like tightly looped compounds, you get very strong magnetic fields being produced, at least for that e-chiral force. Mm. Mhm. Thank you. Oh. Mhm. Yes. Mhm. Yes, and there was some really interesting work done where they used graphene, and they twisted graphene and passed a current through the helical graphene model, and found that you get these CISS effects based on the degree to which you twist the graphene, and totally achiral graphene, its conductivity was reduced compared to the twisted graphene. I think hmm, well, they produced nanotubes of the graphene, and I'm actually not sure how they directly twisted it. Maybe some like some binding to different sized. Uh, hmm, yeah. Yeah. Um, mhm. Aside from the graphene and then the ones that were used, no, not really, not too much on polymers. Hmm. 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 Yeah. Hmm. Yeah. Hmm. Hmm. I'm not sure. They did use the polyalanine here, like polymer, but I'm not sure if there's been further investigations into these the chiral, I mean conducting polymers. Yeah. Thanks. Thank you, everyone. Thank you. Hmm. Okay. Okay. Thanks. Oh, well, that's like really, really.